Assalamu alaikum everyone. So digital logic design, right, and course number EEE241. So my name is Sajjad Ali Mushtaq, right, and I can be reached at sajjad@ciat.net.pk. You can also reach me at sajjad.mushtaq@ieee.org, right. So I will be teaching you this course, right, and we will be having 32 lectures, right. So before starting, let's introduce myself, right. So I did my master's in electronics from Quaid-e-Azam University in 1999, and immediately after finishing my master's, I switched to the professional career, and I started my career as a system administrator, right. So after some time, after working for around 2 years at Hamdard University as a program coordinator and system administrator, I moved to CIAT Ahmedabad and started my job there as a project manager, right. So I switched my career to software development and project management, right. So from 2001 I worked there for around 6 years, right, during that time span I improved my education. I again joined Quaid-e-Azam University and did my MPhil in electronics, right, and during my stay at CIAT, we did a lot of different projects, right. Some of the projects that includes National Testing Service, right, and campus management system and university management system, right. So in 2006, right, I moved to France for higher education, right. So I did my PhD there, and after finishing my PhD, I rejoined ComSats in 2012, right. So I will be teaching you digital logic design, right. So let's start. So before starting, so let's talk about something about the title, digital and logic design, right. So as you know that most of the quantities that we have to come across over this universe, they are analog, right. So like temperature, pressure, and there are there are certain number of natural phenomena that are analog, right. But in order to have the accurate, right, system, right, we have the digital world, right. So the best example that we can have is the computer system, right. So you can see that or you can think about different other systems that are basically based on the digital system, right. So the other word, that is the logic design, right. So that includes different concepts, tools, right, and those tools and those concepts, they are actually used in order to design the hardware, right, and that hardware or those different components, the base of those different hardware and components is the logic, right. So we can have different logic circuitry in order to perform addition, subtraction, multiplication, and so on and so forth, right. So we can also have a circuitry that can perform certain logical operations, right, and or not, and so on and so forth, right. So we need to develop a discipline in order to accommodate those different analog processes, analog quantities which we come across while we are living on this universe, right. So because there are certain advantages that we have over the analog system, right. So that's why we have introduced the digital logic design, right. So as you know that there are different quantities that we have to represent, like if we talk about the analog quantities, temperature, pressure, and so forth, right? So similarly, we have to represent the digital quantities, right? So, and we need signals, right? So and our digital logic design is actually based on the binary system, right? So as opposed to the decimal system which we are using in our daily life, right? So there are certain justifications, certain reasons that why we are not using decimal number system or decimal, or our system is not being designed on the basis of the decimal number system or decimal system which we are using in our daily life, right? So one of the key justification or the key point is that if I talk about a binary number system, so we have two values, right? 0 and 1, yes, no, on, off, right? While on the other hand, if we talk about the decimal number system or decimal system, we have 10 different values starting from 0 to 9, right? So if I want to design a system, if I want to devise a system that is based on the decimal system, number system, then I have to handle 10 different voltage levels, right? So imagine the complication as compared to the digital number system or binary number system, right? So this is the key justification, right? So we have to handle only two values when we talk about the binary system, right? So here we have represented two different values or two different states. We have one, we normally call it high in logic, right? Or H, or on, right? So for 0 we have logic low, or L, or off, right? So they are in binary formats, right? So binary 2. So this is the good example, right? So we can have light on and off, right? So here we have on, and here on the right hand side we have the off, right? So we can also have power switches, right? So on and off, right? So let's before going into more details, let's talk about the evolution of the digital logic design, right? So that discipline actually came into existence when a mathematician, right, George Boole, right, he presented his paper on an investigation of laws of thoughts, mathematical theories of logic and probabilities in 1854, right? So that paper was the second one, and that was presented in 1854, right? So, and he presented his first paper on mathematical analysis of logic, right? So before that there was no existence of logic or no evidence of logic, right? So after the first paper he presented another paper in 1854, right? And at that time span George Boole was not able to get recognition of his proposed logic or proposed work, right? So it was Claude Shannon, right, who reused the George Boole's work, right, and he used his work or his proposed idea in a symbolic analysis of relay and switching circuits, right? He used Boolean logic and Boolean algebra, right? So it was Claude Shannon who you can say revisited the logic presented by George Boole, right? So that thesis was his master thesis, and that thesis is considered one of the best theses of all times, right? So because he is a very renowned scientist and he proposed a lot of different communicational concepts and ideas, right? So that was considered the beginning of the digital age, right? Or you can say, in other words, the computer age, right? And then on the basis of that work done by Claude Shannon, the machines that were designed on the basis of that logic, they were used in the Second World War, right, in order to calculate different paths, right. So then another English man, right, who proposed the idea of state machine, right. So rather than having simple computational power, we can also have the control, right. And there are some motivational factors, right. So you can have an idea that the semiconductor industry, it has grown tremendously, right. So this is the basic requirement, right. So all the digital logic or all the circuitry or computers, they are being manufacturing by using those materials, right. So this industry, it has grown tremendously, right. So in today's appliances, you cannot escape microprocessor, microcontrollers. Every device, every appliance has microprocessor or microcontroller or some sort of digital circuitry inside, right. So we cannot, whenever we talk about the internet, we talk about the cell phones, gadgets, tablets, right, even we talk about the health facilities, we cannot escape the digital logic design, right. So it's present everywhere, right. So these are the motivational facts that we can think about, right. And after this short and brief introduction, right, so these are a few of the bullets, right. So that we will be trying to discover or discuss or study. First, we will be discussing the number system, the use of number system and the conversions, because we can convert a number from one number system into another number system, right. So then the basic building block of the digital system, and after that we will be discussing the laws, axioms, right, and the algebra, Boolean algebra, right, and then minimization techniques, how we can minimize the circuitry, right, and then we will talk about the combinational and sequential circuitry and what are the differences, right, and the application of the combinational and the sequential circuitry all together, right. And then we will talk about the circuit analysis and circuit design, and this is again important, state minimizations, right. So whenever we talk about the combinational circuitry, we have to think if a function can be performed with 20 gates, right, or 20 components. So after the minimization or simplification, the same functionality can be performed by 15 gates or maybe less, or maybe right. So we can have an idea, right, that how important the minimization is, right, in case of combination circuitry. But when we talk about the sequential circuitry, right, so sequential circuitry, in sequential circuitry or sequential logic, we also need to perform minimization, right. So here we cannot minimize the number of gates, rather than we can minimize the number of states, and those states are being stored by the flip-flops, that are the storage elements, right. Then we will talk about different ICs, maybe the data sheets, but we will not be discussing the methodology, how ICs are being manufactured, right. And finally we will utilize all the learned skills, right, and ideas in order to design different circuits, right, and different designs in order to have realization, right. So lastly but not leastly, we will be following a software, right, or we will be learning a software in order to have the simulation, because this is very important for the students whenever they are learning remotely, right, because this is not feasible to go into the lab daily or on fortnightly or maybe after a month or so. So what we can have a computer software which you can have at your own personal computers or desktops or laptops, right? Or you can also have the facility within your study center, so you can implement your ideas, right? You can design different circuits and you can analyze and evaluate those different designs and concepts by using the software, right? So this is very handy and this is very effective, right? And this is the textbook, right, which we will be following. I have chosen two textbooks and I declared one as primary text, right? That is Digital Design by Marismano and Michel, right? And then this is the complementary material, right? Logic and Computer Design Fundamentals, again by Marismano and Charles, right? So you can go through other books. There are no limitations, right? There are no restrictions if you want to read more books, right? But I will be trying to follow this primary text, right? So I will follow this textbook whenever we will be going through 32 lectures, right? So let's start lecture number 1, right? So number systems, right? So as I have mentioned that we have different number systems that are available now, right? So as decimal is the number system which we use in our daily life, right? So and binary number system is being used for computer design, right? And the octal number system is being used, right? Again within the computer, but not regarding the design and the analysis, right? So we can see that it is being used within the operating system whenever we talk about the permissions, right? So if you have a file and you want to restrict the read, write, execute permission, so you normally use the octal numbers. Then hexadecimal number system, right? So it's again being used, right? So if we talk about the MAC address, right? So we have an interface, Ethernet interface on every computer, and when we talk about the address, so those ports or interfaces, they are addressed by using hexadecimal, right? So these are different number systems which we are familiar with, and they are being used differently, right? So whenever we talk about the design of the computer system, right? So we have to start from the number system, right? So as mentioned, that binary number system is the basic building block for the computer system, right? So ultimately on the basis of that number system we devise different or design different circuits, right? So and then we are building different computing machines, right? So digital systems, right? So what are the pros of digital systems? If there are certain limitations or cons, then we will be also discussing the cons of or disadvantages of using digital systems, right? And decimal system, right? And binary and octal number system, and then we will be discussing the conversion between different number systems, right? So let's talk about analog versus digital, right? So if we have a tap, right? So we will take a very simple example, right? So when we think digitally, right? So water can be flowing or not, right? So you can switch on the tap, right? So water will start flowing, right? And if we switch off, the water will not be flowing, right? So we have two states, on and off, right? So we cannot think about the intensity of water, right? The amount of water, the pressure of water, right? And the hotness and coldness of the water, how much it is hot, right? And how much it is cold, right? So if you talk about in an analog fashion, right? So you should think how much water is flowing out of the tap, right? So there are certain advantages of the digital system, right? First one is the replication, right? So it's very easy to replicate, right? So if we take this example again, so it's very easy to make it on and off, right? So if you think in analog way, right? So if you open the tap first time and you want to note down the flow of water or intensity of water, right? So it's difficult to achieve the same flow of water, right? Whenever you turn it on second time, right? So it's very difficult in order to have replication whenever we talk about analog system, right? So here you can see we have the diagram. This is digital and this is analog, right? As you can see, this is time and this is V, right? So error correction and detection, right? So it's easier in digital system to detect an error and then correct an error, right? We can also have programmability, right? So program capability, right? So you can take the example of digital computers, right? So they are easily programmed, right? Right? So we use two discrete values, right, in digital systems, like we will be using binary number system, right? And we can use different mechanisms in order to represent those two values. Sometimes we represent those values by using level of the voltage, right? So if I go back, so you can see that this is +5 and I have taken this as 1, this is -5 and this is 0 again, right? So and this is the level of the voltage, right? So voltage, time, and this is the level of the voltage. And sometimes you use intensity of current, right, in order to represent those ones and zeros, right? So here you can see that we have voltage, right, and this is low, and low is from 0 to 0.9 and high is from 2 to 5.0, right? So this is the gap, right? So we can always have some other pronunciations: 1 0, on off, true false, high low, head tail, black white, right? So here is the comparison between the analog and the digital system, right? So if I talk about the storage capability, right? So in case of analog, we have limited storage capability, while in case of digital we have. So you can think about the videotape, right? So you have a very big size of the videotape and look at the amount of data. On the other side, if we talk about the flash memory, right? So it is smaller in size, and even despite the size, it can store enormous and huge amount of data, right? So this is one of the advantage, right? And then we have accuracy, right? Here you can see that analog is not very accurate. On the other side, digital is accurate, right? And there are a number of comparisons, and you can go through those comparisons, right? So let's talk about the digital computer system, right? So it consider discrete amount of data, right? For example, 26 letters in alphabet, 10 decimal digits, right? And we can build the larger quantities, right? For example, if you want to represent a string, right, that is composed of a large number of letters, we can do that, right? Similarly, if you want to have a number of more number of decimal digits, so you can do that, right? So this is we already discussed, right? Computers operate on binary, right? And it's easy to represent and handle the binary values electrically, right? So voltages and currents can be implemented using circuits, right? So let's talk about the decimal number system, right? So they are 10, right? So starting from 0 to 9, right? And why we use decimal number system, right? So if you look at your hands, right? So and you count the number of fingers, right? So they are 10. So this is very basic and natural and very simple justification that why we use decimal number system in our daily life, right? And because it's natural, right? So this is a sort of evolutionary process, and you can see that we have 10 fingers for majority of the human beings, and there are exceptions, and exceptions are always there, right? So if I want to know how many items does a decimal number system represent, right? So you can see that we have 4-digit decimal number, right? So how many? So each decimal digit, right, in a specific position has a corresponding weight, right? So these are units, and these are tens, hundreds, and thousands, right? So that's why we have multiplied 3 by 10 to the power 0, multiplied by 5 by 10 to the power 1, units, tens, hundreds, and thousands, right? So this is the way out, right? How we justify or how we manipulate that how many decimal numbers we can represent with this string of decimal numbers, right? So here we have fractions, right? So the same methodology or mechanism is adopted till the decimal point, right? So tens, units, tens, hundreds, thousands, right? And then 10 to the power 4, and after decimal point you can see that we have 10 to the power minus 1, right? So minus power is rising, right? So it's raising. So here in formal notation, but we place this, and we have a 10 at the base, right? So similarly here we have the octal number, right? So they are 8, right, starting from 0 to 7, right? So and here we have the same mechanism as we have in the decimal number system. So as you can see that we have 8 to the power 0, 8 to the power 1, 8 to the power 2, and 8 to the power 3, right? So 0, 1, 2 power is rising. This is the least significant digit, and this is the most significant digit, right? So we started from 0 and we are raising the power by 1 as we move on, right? So here fractions are handled in the same fashion, right? So after the fraction, the negative powers have started and it is raising, right? So they don't include 8 and 9 that are included in decimal number system, right? So let's talk about the binary number system, right? So that is the number system that the computer is using, right? So our computer is designed on the basis of this number system, right? So we have binary digit bits, right? So how many items does a binary number represent, right? So here you can see that we have the binary number 1011, right? And binary mean 2, right? So as we have decimal base 10 and octal base 8, so we normally started raising the power of the base, right? So here base is 2, so 2 raised power 0, 2 raised power 1, 2 raised power 2, and 2 raised power 3, right? So you can see that it represent 11, right? So if I start here 1011, right? 2 raised power 0, 2 raised power 1, 2 raised power 2, and 2 raised power 3, right? So this is 0, So how, or you can say that we have 1, 2, 4, 8, right? The place where we have 0, we will ignore it, right? Other has to be added, right? So 8 plus 2 plus 1 is equal to 11, right? So this is another way out, right? So how we will be handling fractions? So same methodology, right? After the fraction, we will start, right, multiplying by 2 raised to the power minus 1, and this is 2 raised to the power minus 2, right? And if we group those different bits, right, and we have 8 bits, then those 8 bits are called a byte, and a group of 4 bits are called a nibble, right? So again, a justification why we use binary number system, easy to represent zeros and ones, right? So it is more immune to noise. It can tolerate more noise, right? So this is the gap or transition. You can see there is a huge gap between 0 and 1, right? So if we have 3.1, still it will be considered as 1, right? If we have 1.1, still it's considered as 0, because this is the sort of immunity or tolerance against noise, right? So we can easily transmit data, right? So it's easy to transfer 2 levels, right, as compared to transferring 10 levels for decimal number system, right? So as representation is easy and we have to handle 2 levels, so it's easy to design the circuitry, right? So here is the example: AND gate 1 0. We have 0, right? Okay. So these are the conversions, right? So base 2 and base 10, right? So here we have base 10, 0 to 9, and for binary we have base 2, right? Right. So binary as a voltage, right? So we can also have a switch, right? So here is a very simple example. This is a voltage, right? This is ground. So if this switch is connected here, so we will be having VCC at the output, or you can say that we have 1, right? On the other side, if we have connection here, that is ground, right? So ground is normally 0, so we have a 0 at the output, right? So this is the representation of ones and zeros. So here 1 and 0, right? So this is a snapshot of the conversion, right? So here you can see that when we talk about the number system, we will always be talking about the conversion on the basis of the computer system, right? So this is the this, you can say, our machine or our computer, right? So you can see that there is no direct path from decimal to octal, right? Although we can convert the number, but as we are studying or talking about the digital logic design, so that logic design is always based on binary number system. So we have to go through this binary number system in order to, although we will see that we can convert a decimal number to a hexadecimal and a decimal number to an octal, and so on and so forth, right? But as if we have a system or we have a circuitry that is designed on the basis of base 2 number system, right? So first what we will be doing, we will be converting to that native number system, right? And then after that we can convert to the targeted number system, right? So you can see we have the binary, right? And from decimal to binary, and then binary to octal. If you want to convert a decimal number to a hexadecimal number, first you have to convert that decimal number to binary, and then binary has to be converted into a hexadecimal number, right? And these are different number systems, their bases, symbols, and the utilization, their utilization system. Decimal number system, it is a base 10, right? Symbols, it has 10 symbols starting from 0 to 9. Used by humans, yes. Used in computers, no, right? Binary, right? Base 2, symbols we have 0, 1. Humans are not using, right? And computers, in our computer is actually based on this binary number system. Then octal, right? Base 8, right? And here we have symbols, no, right? So actually on the design level it is not used, on the application level, yes, we are using this octal. So again, hexadecimal, base 16, and 0, 1 up to 9, and in place of 10 we have A, 11 for B, and 15 for F, right? Used by humans, no. From the design point of view, no, but from the application point of view regarding the computer system, yes, right? So this is the conversion I was talking about, right? So here we don't have any machine or any circuitry that is being designed on the basis of the binary number system. So you can see that we have arrows everywhere, right? You can go from decimal to binary, from decimal to octal, octal to hexadecimal, right? And these are the crosses. If you want to convert a binary number to an octal, yes. Hexadecimal to decimal, yes, right? So these are, so let's talk about the conversion, right? So here we have a decimal number, right? And we want to convert that number into a binary number system, right? So that's why we are dividing it by 2, that is the targeted base, right? So we have decimal number, right? And we want to convert that decimal number into binary number, right? So what we need to do, divide by 2, we have a quotient and remainder, right? So here we have 6 and we have this remainder, right? So 6 will go here and we will again divide. This is the quotient and this is the remainder, right? And here again 3 will go here, move here, quotient and remainder, right? 1 will move here, so we will keep it up, right? Or keep going on till this right will be is non-divisible, right? So 1 is not divisible by 2, right? So we have a 0 here and this is the remainder, right? So you can see that here we have 1, 1, 0 and 1, right? So we will move like this, right? Right? So you can see this is the most significant bit and this is the least significant bit, right? So we have 1, 1, 0, 1, right? So if I want to convert that into decimals, so this is 1, this is 2, this is 4, and this is 8. So as I have mentioned, 0 will be ignored, right? So 8 plus 4 plus 1, 13. We will have 13. Right? So how we will be handling the fraction, right? So you can see that for fraction, right? So this is the decimal fraction, right? Base 10, and we want to convert that fraction into binary, right? So multiply by 2. So as opposed to division, for fraction we will be multiplying by 2, right? So this is integer, right? And this is the fraction, right? So that fraction will go here and we will have no integer, right? And this is the fraction go here, 1, right? And we have a 0. So when we have a 0 in the fraction, right? So it means job done, right? So 1, 0, 1. This is most significant and this is least significant. A is, that's why I placed -3, -2, -1, right? So after 0, right? So here we have to go like this, right? So you can see 0.101, right? -1, -2, -3, right? So these are the conventions, right? So 2 raised to power 8, 256, right? 2 raised to power 20, 1 mega, 2 raised to power 30, 1 giga, and we have tera, 2 raised to power 40, and peta, and so on and so forth, right? So this is the growth. So normally when we talk about the computer system, so we need to perform certain operations, and those operations, they are addition, subtraction, multiplication, and division, right? So let's talk about the addition whenever we have binary numbers, right? So these are the two numbers that has to be added, right? So here you can see 110 and 1 is carry, and the carry will move here. 110 carry will move here. 110 plus 1 1 carry move here. 110 carry move here. 1 carry move here. 0 carry move here. 1, right? So this is the binary addition, right? And then we have binary subtraction, right? So we have to subtract this number from this number, right? So 110, right? So here we have 0 and this is 1, so we will be having a carry here, right? So you can say 2, right? So 1, here we have 0, carry will be taken, right? Borrow, right? Not carry, borrow, right? So we will borrow, right? So here what we will be having, right? 2, 1, here we have 0, 0, right? And again here you can see, right? So here this has to be borrowed here and here, right? 2, 1, so here we have 1, right? And 0. So this is here we have carry when we talk about addition, and here we have borrow when we talk about the subtraction. Here the multiplication, right? So this has to be multiplied with this, right? So first all those bits will be multiplied by 0, and then we will left, we give the data shift left, right? So this is a shift left, and 1, we multiply all these bits with 1, right? So it will repeat zeros, again shift left, and here again shift left, and after that we need to add, right? 1 1 0 carry 0 carry 1 carry 1 1, right? So this is the answer of binary multiplication, right? So here we have to convert an integer from decimal to octal, right? So we have the decimal, and we need to convert that decimal number into an octal number, right? So 175 base 10, so the target base, right, 8, so we will be dividing by 8. Quotient, remainder, that 21 will move here. Division, after division we have 2, and this is the quotient, right? 8 2s are 16, and we are left with 5. 2 non-divisible, right? So now it's 0, right? And we have the quotient. So 257, right? So 257, and with the base 8, right? So here we have the fraction, right? So if we want to convert, so here you can see that we are converting actually, right, the decimal number to the octal number, right? So if I go back, so here we have the option decimal to octal, right? So here we don't have the direct option decimal to octal, right? So first we have to convert, because this is based on the binary number system, so this is why the circuitry or the design, right? Okay, so if we want to handle the fraction, right? So multiply by 8 as opposed to the division, right? So this is integer and this is the fraction, right? And here again 4 0, so we will be having 2 4, right? So we will be moving like this, right, from top to bottom, right? That's all for today's lecture, right? So today we talked about the introduction, right, about the course, right, and we will be actually having 32 lectures, right, and we talked about the textbook which we will be following, right, and we also talked about the complementary material which you can go through whenever you will be preparing for this course, right? And then we talked about some of the details regarding the course contents. We will start from the number system, then we will move on to the Boolean logic, right? And before Boolean logic we will be discussing the number system, right, and the conversion between different number system. Then after that we will be switching to Boolean logic, different laws and theorems and some axioms of the Boolean laws, right? After that we will be focusing on the minimization techniques, right, that how we can minimize the possible number of gates, right? And then after the combinational circuit analysis and design, we will switch to the sequential circuit analysis and sequential circuit design, right? And the sequential circuit design and analysis is very important, and we will be then discussing about counters, registers, flip-flops, and so on and so forth, right? And the design, the actual design, right, of the circuitry. Then we will talk about different memory elements, RAM, ROM, arithmetic logic unit, and so on and so forth, right? So these are the brief course material introductory topics, right? So after the course introduction, right, so we discussed about the comparison, right? So why we need digital logic design, right? So then we talked about the evolution of the digital logic design, right? So actually its evolution is very interesting, and it started way back, right? So when George Boole actually proposed the idea of the logic, so he unfortunately he was not able to get recognition, right, unless Claude Shannon, who reused his work, right, when he was doing his master thesis, and that thesis have changed the communication world, right? So in today's communication we have a lot of different theorems, lot of different laws from Claude Shannon, right? So after the evolution, right, so we discussed why we use binary number system, right, or why we prefer digital, right, as compared to analog, and why we use binary number system as compared to the other number systems. Though there is the fact, right, that we should accept that in our daily life we are using decimal number system when we talk about the counting. In everyday's life we count, we represent, and we intercommunicate, right, by using the decimal number system. So one of the biggest justification is that if we talk about the decimal number system, we have to handle 10 different voltage levels, and because in decimal number system we have 10 different values starting from 0 to 9, right? So if you think about the decimal design or design that is based on the decimal number system. So imagine that you have to represent the 0 by a level, right? So there should be a guard, or there should be a splitter between the level, and then you have to represent 1 with another level, 2, 3 and 4 and so on and so forth. So you need 10 different levels, right? So it's difficult. And imagine the complication of the design, right? So even if you want to design an adder, right, or some other simple circuitry that can add 2 decimal numbers, right? So imagine the complication of the design, right? So on the other side, when we talk about the binary number system, so we have only two values, 0 and 1, right? So we need only 2 levels. For example, we represent 0 by, for example, the voltage level of that is between 0 and 1, right? And then we represent the binary number 1 by the voltage level that is lying between 3 and 5, right? So we need 2 voltage levels, right? So that is the solid and very key justification that why we are using binary number system as opposed to the decimal number system, though we are using decimal number system in our daily life, right? So after the justification, right, so we then talked about other number systems and their utilization, right? Starting from octal number system, and the octal number systems, they are not being used in the design of the computer system, but they are used within the computer system regarding the application, right? So whenever we talk about the permissions of files in Linux or Unix, right, so we need to restrict the access, right? So for that we use octal, right? So you have seen that that we have read, write, execute permissions, right? So we are using actually octal number system. And then we talked about the hexadecimal number system and its utilization, right? So hexadecimal number system, it have 16 numbers, right, starting from 0, right, and till 9. It's the same as the decimal number system is, right? So we replace 10 with A, right, 11 with B, right, and we have 15, F for 15, right? And in the octal number system we have 8 different digits starting from 0 to 7, right? So regarding the application of the hexadecimal number system or numbers, right, so they are not involved directly regarding the design of the computer system, right? So you can see when we have the address of an Ethernet port, right? So those 8 different numbers, right, they are in hexadecimal number, right? So I don't remember the exact number of hexadecimal digits, but the MAC address or the Ethernet hardware address is represented by using the hexadecimal numbers, right? So this is the utilization of hexadecimal number system, right? So even sometime whenever we saw the registry within the Windows operating system, right, so you can see that there are certain values that are being filled with hexadecimal numbers, right? So this is another utilization of hexadecimal number system. And then we have seen the conversion, right? So this is very important, right? So whenever we talk about the conversion, right, so we have two school of thoughts, right? First, if you are going to use a circuitry that is actually based on the binary number system, so there is no direct way of the interconversion, right? So first, if I want to convert an octal number to, for example, decimal number, right? So what I need to do, I need to convert that number, octal number, to the base 2 number, because this is the native number system, or this is the native circuitry that I have to use. So I will convert that number to the base 2 or binary number, and then from binary I will convert that number to the decimal number. Similarly, if I want to convert a hexadecimal number to an octal number, right? So there is no direct way if we talk about the binary circuitry or binary design, right? So we are relying on the circuitry or design that is based on binary number system, right? So from hexadecimal to octal. So first I will convert that hexadecimal number to binary, and then that binary has to be converted to the octal number, right? So this is the interconversion between different number systems when we are relying on the system or on the circuitry that is designed on the basis of binary number system, right? But on a piece of paper, right, or on the basis of different methodology or mechanism, we have the option. For example, if you want to convert a binary number system or hexadecimal number system to an octal number system, right? So hexadecimal to octal, right? So we can do that straight away, right? So we have the method and the mechanism available, right? So, and then after the interconversion, right? So obviously when we talk about the computer system, so our computer system, it has to perform certain operations, right? And those operations, they include addition, subtraction, and multiplication, right? So we talked about, we are familiar with the decimal addition, decimal subtraction, and decimal multiplication, right? We are not aware of the binary addition, binary subtraction, and binary multiplication, right? So in this lecture we talked about how we are performing binary addition, right? And how we will be because you know that we have a new idea of carry, right, regarding the binary system, although we know the decimal, right? So here you can in the binary number system, you can see that we have the carry, right, and the carry moves move forward over the slot where where the corresponding bits has to be added, right? So we perform binary addition and then binary subtraction, and we have seen the concept of borrow, right? Similarly in addition, right, in multiplication, we have seen that each time we multiply, we have to give a shift, right? And after the corresponding bits are multiplied, right, with the multiplier, right? So we have to perform the addition, and we follow the same mechanism of addition, right? So that's all for today's lecture. So अपना ख्याल रखिएगा, मेरी तरफ से अल्लाह हाफिज़, अस्सलाम वालेकुम।